To the very loud Seamless Astronomy Colloquium, first one of the 2015-16 academic year. And today I'm honored to introduce my friend and colleague Nick Holloman. Some of you who remember the IIC will remember that Nick was here before. Nick spent a lot of time with us here helping Mike Halley and Michelle Borkin and other people here, and I tried to visualize astronomical data in 3D. But Nick does a lot of other things, and he started out his career as an undergraduate in Durham doing computer science, and he went to graduate school in Leeds and learned a lot more about parallel computing. And then he went to industry, and he actually developed some of the technologies that you see in Sharp 3D TVs. And he gave us a lovely 3D laptop. I don't know where it is. We have to find that thing. I love that thing. We have a laptop that has a 3D screen. We did. I lent it to Michelle. Uh-oh, Michelle, this is on video now. Anyway, speaking of video, before I continue about Nick, I'm supposed to point out that there's a hashtag for this talk here called Seamless Big Data. And if you want to thank Nick on Twitter, it's kind of written behind the podium here, but it's on the back too. He's Binocularity on Twitter. Okay, so anyway, what is Nick doing and what is Nick going to talk about? Let me finish. Wait, we left him at Sharp. Right, then he went to Durham, where he was faculty member, again working on 3D stereo visualization. And then there was a brief foray to Leeds because he hadn't explored enough of Northern England. And then he went now back. He has a new position as of July as a professor of visualization at Newcastle, where they've started a very extensive program that we should ask him about in visualization, training people to do this in graduate school and do research in visualization. But Nick's love is to connect the technologies for seeing data to how people actually see data, to understand the cognitive and psychological principles associated with that. And in this era of ever increasing data set size, Nick is trying to also apply what he's learned so far and what other people have learned to really big data sets. And today he's going to tell us all kinds of interesting things, I understand, including visualization of a data set that has to do with something that happened in the Middle Ages. So I will stop now and give you Nick. Thanks, Nick.
So, good afternoon. Thank you, Alyssa, for your hospitality and invitations and all good things this week. So I'm going to talk today a little bit about visualizing big data, some evidence on some of the things that we've done and some of the futures. And because I've started a new job, I'm afraid you'll have to put up with me in a more reflective mode than usual. It won't be all evidence, some of it will be a bit speculative, and you're quite welcome to interrogate my speculations thoroughly, and I hope you will. So currently I've just joined an institute at Newcastle called the Digital Institute. It's part of a new initiative. Some of you may have heard of Newcastle Brown Ale. It's very popular in America. Not so much in the UK. We demolished the brewery and we're now putting something called Science Central on the top of that. And that's where our new urban and computing sciences buildings will be. So that's where I'm located now in this very nice new core building they've just built. And the aim of the Digital Institute is to be a centre for multidisciplinary expertise across the university. So to include scalable computing, security, cloud computing, now I'm there, visualization, and it has a very strong link to the statistics group and does Bayesian statistics, machine learning, and deals a lot with streaming data. The director, some of you may know, is Paul Watson, who won the Microsoft Jim Gray eScience Award last year, and has been a long-time advocate of multidisciplinary work in eScience in the UK and abroad. And one of the long-term goals is to transform the way the university does research and impact using digital techniques. So alongside my research goals and aims, there's also this aim to bring visualization to people across the university. And I'm not going to say much about that today, but that's one of the things I do. The Institute's brought in 100 million in research in the last 14 years or so, and has two big projects at the moment. One is a cloud computing centre, Cloud Innovation Center with Red Hat and Microsoft to bring cloud computing to science and technology people. And the other is a Center for Doctoral Training, where we're training people in computing and statistics to be able to do data analytics and visualization. So we've got 50 grad students coming in over the next 5 years to be trained in that area. So there's quite a lot going on in the Institute. And I'm there, well, they made me an offer I couldn't turn down, so I'm there with my new toys to play with. So what should I talk about today? So part of my reflectiveness, I'm worried about what visualization is and why we should do it. And so I'll speculate a bit on what I think of that now. I'm going to look at some evidence. Last time I was here, I talked about stereo 3D visualization of cosmology data. And we evaluated how people respond to some of these visualizations. So I'm going to talk about that. And then I'm going to go off on a wander into the future and how we might change visualization in the future using larger scale cloud computing techniques. So, visualization. I need a timer here. I've got one up there. So what is visualization? I spent some time, you won't believe quite how much time, trying to visualize what visualization is. And this is the result. So the concept for us is to go from big data to big ideas, where we efficiently and accurately generate some insight and understanding to support decision making. Usually you want visualization to make a decision about something, whether to publish a paper, whether to change the traffic flows in Newcastle, whatever the goals are. And some set of digital data whizzing in from somewhere, in our case from the cloud. I spent a very long time drawing that cloud for you. And hitting the screen and being visualized into, in this case, one of the Eagle galaxies. And the bit I'm then very interested in is this connection to the human being. How do you present data in such a way that people can understand it and understand it accurately? And generate ideas in their heads. I mean, we're literally putting ideas into people's heads in visualization. And so if you're doing that, you want to know that these things are accurate and reliable and work well. And have some meaning for the people involved in looking at things. So that's kind of where I think visualization is. There's a certain group of visualization people at the moment who think it's about information theory. And I couldn't really disagree more. Information theory is about coding and about what you can and can't compress, really. Visualization is much more about what you can get into the brain and how to use the human senses to make that in some way more efficient and easy. So what roles can visualization have? And you might want to think of your own and tell me now or later what it should be. But as far as I can see, there's at least these 4 roles that visualization might take up. It's about describing and explaining ideas to people. And we do a lot of this in entertainment, but also in learning and outreach. So a lot of the visualizations I've produced in film form are presenting cosmology and astronomy data to teenagers. Usually, first place, so that's the Royal Society Summer Science Exhibition, but then around the world in different places. Second route for a role for visualization is in monitoring information streams. You'll see later that I'm currently very interested in the Internet of Things and data coming from sensors. Whether I can say they're larger scale sensors than telescopes, I'm not sure, but we'll find out in a few years. But certainly if you want to monitor for events and information streams, visualization can play a role there. Alerts and warnings are part of that. Very often it's an exploration and about analysing information and seeing what's there. We were talking earlier with some grad students some of whom are here now, about that as a role in their research, how they use visualization to guide their search for information and meaning within the data they have before they go off and quantify it in more detail. And that's very much in the style of Tukey's work on exploratory data analysis in the 1960s and 70s. And we've used that in public service data recently, looking at school flows of pupils between schools. And then often it's also about a more creative thing, creating and testing hypotheses in science and elsewhere. And the cosmology simulations have used this to an extent at Durham, not a lot, but to an extent. People have often said, when you've put up, some of you will know about the 2DF survey of galaxies, and when we first visualized it, the astronomers came in and said, wow, that's very thin. I wonder if our statistics hold up, as they saw the thinness of it when it rotated around. So testing hypotheses with visualization is another route. And of course, things might have all of these, or one of these, or some other role that you might think of. Okay, so that's on what visualization is, at least what I'm beginning to think it should be in the future. What's the evidence that visualization is useful to us? This story goes back more than 10 years, when we started producing visualizations of astronomy and cosmology data with the ICC at Durham. And this is really the end point of a train of research going from creating algorithms to draw pictures, producing films using those algorithms, and then putting those out into the public domain, and eventually testing if they were doing something. And I'll say what the something might be in a second. This is a paper we published in IEEE Journal of Display Technology last December. So the question is, if we're going to produce these visualizations, why not produce a number that says yes or no, or right or wrong instead? And we looked at whether it's worthwhile doing this in the context of my work on stereo 3D. I'm not only interested in stereo 3D, but very much interested in stereo 3D. And in particular in the context, I'll show you a movie in a second, visualizing cosmology and astronomical data. I'm going to go back in time a bit. I'm sure you all know what a stereo 3D display does these days. You need to generate two pictures for one. You fuse them together. Gives you a sensation of depth in the picture. Gives you a single mental image in some sense. I'm going to talk about what is and isn't a high quality picture, but I'm not going to define it in great detail. You kind of have to trust me in a way that I know what a good quality 3D picture is. But one of the things you always have to get right for a good quality 3D image is produce a good quality 2D image, because most of the cues to depth that aren't stereo are found in 2D images. And this was something that, if you watched the 3D TV rise and fall recently, was something that TV manufacturers forgot. They made the 2D image quality in 3D worse than the standard 2D image quality. So they affected all these cues to depth that you'd normally use. So I'm going to skip over this a bit quickly, because it's quite old stuff for me, and also because it's not just the idea of what is and isn't high quality is really what I want to get over. But here's what happens in a stereo picture. You have two pictures. These are overlaid on each other, one for the left and the right view. And there's some disparity between corresponding points in those two pictures. So the same points projected to a different position on the plane in each image, depending on how far away it was from the camera. And that signal of disparity is what gives you the sensation of depth when the images are played back on a display. As is shown in this picture, the 2 points are on the right on the screen. Your brain sees one point through one eye, the other point through the other eye, and generates a perceived point somewhere in space, and in this case behind the screen. If these are crossed, you also see depth in front of the screen. There are various interesting issues related to that 3D images are not very portable in the same way 2D images are, but we don't really need to worry about that today. So we had this model of how disparity works. We then went off and measured people and how you see in 3D. And unfortunately, there's a great variation in how much depth different people can cope with. So the hardest conditions on the left. So this is a person looking at a screen plane. Black bars are depth in front of the screen, white bars are depth behind the screen. And it's showing how much depth each individual could cope with before they lost fusion and didn't see the stereo effect anymore. And if you look at the values down here, which are in meters, for some reason it should be in centimeters, it's around about 10 to 20 centimeters of depth each side of the screen. So the big problem with stereo displays is you can't show an awful lot of depth on them. And in the real world, even in this room, there's several meters of depth, and if I were to take a picture of you and then put it on a screen so it was within a range that people found comfortable to watch, I'd have to squash it up a lot to do that. That was with a very demanding visual stimulus, a black on white image. With slightly more realistic images of textured boxes, you could show more depth, but even so, you'll notice here subject 3 could only see plus or minus 15 centimeters of depth comfortably on a 3D display. And these were all people who'd been screened for normal vision, so there was nothing we could measure that was wrong with their vision. There's just quite a wide variation. So this understanding of how people see in 3D led us to develop algorithms that controlled depth in certain ways, so that when you took a 3D picture, you could kind of guarantee it had a certain quality in depth terms when it got onto the display. And in this case, by quality, I mean that most people should be able to see it without feeling some kind of stress in their eyes. I'm not sure I need this slide, but this led in Hollywood to a concept of depth budget, where all films are filmed to keep the action within a certain range either side of the screen plane. And what we called, back in the other slide, a range of geometric perceived depth has become known as depth budget. So you have to work within a certain depth budget, in the same way you work within a certain colour budget or a certain luminance budget if you're filming things. And so we built a set of algorithms which controlled the way in which cameras operated so that they could take a picture of a scene and guarantee, in some sense, that the resulting picture that you saw on a 3D display had a certain quality in it. This, as you'll see, was a long time ago. But so in this case, the scene has a certain range. The display can only show a lower range. And so along the z-axis, the depth is compressed in some sense. And this depth compression leads to, of course, a change in shape. But in fact, you're quite insensitive to that. As your eyes move around all the time, you're changing the way you see in depth, and your divergence point's changing. So you're actually pretty good at coping with this, unless you want to judge veridical size and shape, which in most Hollywood and games platforms you're not so worried about. And this led to a whole set of algorithms which were patented and used in all sorts of films and things. The very first one was Beowulf. It was also used in Meet the Robinsons and other things. Anyway, the point is not the algorithms, but that there was a technique for controlling depth which would give us high quality, in some sense, in our 3D films. And that was what we put into the cosmology films that we created over the years. Okay, I'm going to take a slight divergence before I go into the evidence on the films and talk a bit about why I use stereo, just to plug stereo in case you happen not to have a 3D display on your desk already. In a number of application areas, we've shown, and there's a great review paper by John McIntyre in 2014, I think. We've shown that stereo 3D really gives you a measurable benefit in doing things. So in the top one, in 3D gaming, if you're playing 3D Space Invaders, quite appropriate for this audience, coming towards you and you're shooting them, if you don't have stereo 3D, you can't play this game anywhere near as well, by a factor of about 2 in the high scores. So you really need it to judge distance there. A more interesting task for visualization people is the mental rotation task. This is the Shepard and Metzler task, if any of you are psychologists. Are these two shapes the same? Who thinks they are? Okay, who thinks they aren't? Okay, a few less of you. Okay, a lot of neutrals there. So the answer is they are. And when you do that task in your head, it's known as mental rotation. So it's a visualization task. Your head, your mind has to pick these two shapes up, rotate them and see if they fit on top of each other. And if you imagine rotating the right-hand one, for you, it'll fit on top of the left-hand one here quite easily. So there's a whole set of different shapes we generated and tested. And we showed that your scores were always better in stereo 3D doing this task than on a 2D display. So where you're dealing with complex shapes and trying to judge if they're the same, stereo 3D can be a useful tool. And we had a series of experiments like this. This was a kind of space game, although it doesn't look like it here. So Sony Computer Entertainment Europe came to us and said, can you design a game that will only work on a stereo 3D display? Which, when we sat down and thought about it, meant you had to take away an awful lot of cues to depth, all those on that 2D picture you saw earlier. And what we ended up was a spaceship flying through a series of hoops. So the hoops moved across the screen from left to right. And you had to move the spaceship up and down and in and out in depth to successfully fly through a hoop. And you'll see that to an extent we were successful. The high scores in stereo 3D are about more than 3 times higher than the high scores using a 2D or flat display. And I guess it shows that in situations, and this is a bit like threading a needle, situations where you're really required to use depth judgment, stereo 3D can be essential to being successful at a task. But if you were a gamer, you'd have thought stereo 3D should have taken off because you can get high scores and you can beat your friends. And I was always quite surprised that 3D TV for that reason didn't take off in games. But it's probably because most games are not designed to use depth.
What's the Shapiro test?
It's a test of normality in the data. And it's actually, after we used it, we found out it's not widely used because it's not reliable. So.
Sorry.
But if you'd like to use it, it's been known to be used. It allowed us to apply a t-test to the results.
My name is Shapiro.
Oh, I don't think it was your own test. I hope. It was, and no, we haven't used it. Yeah. Okay, I'll skip briefly on then. So there's quite a body of quantitative evidence that stereo 3D is good for certain tasks. And if you're doing visualization involving shape detection or manipulation or shooting aliens, it's a good thing to have. But what we'd got was a set of 3D films we'd made over the years, Cosmic Cookery, Cosmic Origins, and Cosmic Origins 2, which had used these algorithms to produce films that had some kind of good 3D in them, as we claimed. They'd won some prizes at, in the UK and in California, so they kind of experts were saying they were good. And people we showed them to said, wow, that was good. But what we wanted to know was, how can you evaluate whether films are good or not in 3D? And that's what I'll get on to next. But before I do that, I think, time for film. Sadly, there isn't a 3D display here, but you can see it in 2D. So this is one of the films we evaluated, Cosmic Origins 2. Those of you who know who Carlos Frenke is will know he's got various theories on dark matter, which change over the years. So this was a change in the theories of dark matter from the last time we showed something about this. And the narrator on this is Martin Rees, who was the Astronomer Royal in England for a while.
From the start of human history, we've been trying to make sense of the universe and trying to understand our place within it. But at night, where we can see through and beyond our thin blue daylight to the stars, the wider universe is an enigma, a sight that even today asks more questions than we can answer. Over the centuries, we've made great strides. We've learnt that far from being in the centre of the universe, our tiny planet is just one, orbiting an unexceptional star in the fringes of a very ordinary galaxy, adrift in a universe of billions and billions of other galaxies. Building on the genius of scientists like Newton and Einstein, we can even explain how the universe and space and time itself came into being from nothing. But in the last 50 years, we've realized that the predictions of these otherwise uncontroversial laws don't always match with what we actually see in the universe. Cosmologists have calculated that galaxies are spinning too fast to stay together if Einstein's and Newton's laws are applied to all the stars and gas we can actually see in them.
Some physicists have argued that perhaps the laws of physics themselves need to be changed. Intriguing as this possibility is, there really is no justification whatsoever for such a radical assumption. It seems much more natural to assume simply that most of the mass in the universe just does not shine, that most of the mass in the universe is dark matter. The only way we can understand why galaxies spin so fast without flying apart is by assuming that they're held together by the gravity of mass, which, however, we cannot see. This is the main evidence for the existence of dark matter.
Teams of astronomers are using both Earth and space-based telescopes, building ever more accurate maps of the universe we can see, and looking for the telltale signs of the universe which we can't see.
In the past few years, astrophysicists have managed to make a very detailed inventory of what our universe contains. 25%, about a quarter of the contents of the universe, is invisible matter, dark matter that keeps galaxies in place. About 5% of the universe is what we call ordinary matter. That is the matter made up of the atoms of which us, planets, stars are made of. One of the limitations that frustrates cosmologists the most is our inability to carry out experiments. There's really nothing I would love more than to be able to go out into the cosmos, seated with a new form of dark matter, sit back and watch it evolve. We cannot carry out experiments, but we can do the next best thing. We can recreate in a big supercomputer the evolution of the cosmos, create virtual universes in a computer.
Particle physicists tell us that just after the Big Bang, the universe had slight fluctuations in an otherwise uniform sea of intense radiation. As the initial radiation cooled, fundamental particles emerged and dark matter was created, amplifying these irregularities and eventually creating filaments of great mass which attracted ordinary matter.
Over the past few years, through a combination of astronomical observations, new theoretical ideas, and computer modeling, we have learned a lot about how our universe works. And yet, fundamental questions remain unanswered. We know the dark matter must be there, but we don't really know what it is made of. We know the dark energy must be there, but we don't know what it is. Answering these fundamental and fascinating questions is one of the most important, pressing, and exciting problems for science in the 21st century.
Okay, so now imagine that was in 3D, and you shall see the question then is, how do you ask, when we first made this, it was for 14-year-olds at the Royal Society Summer Science Exhibition in London, and about 5,000 of them came during the week or two that it was on. But then you have to ask, how do you measure that in any way worked, and how do you get a measure of subjective responses to these things? So what we looked at was two things, which was partly driven, those of you who've, I don't know if there's anyone from the UK, may have heard of the Research Evaluation Framework, was not unaffected by that, but we're looking at significance. So was there a change in audience attitudes to 3D and the quality of 3D they might expect before and after watching this content? And did this have reach? So could we have it measured in our lab? Could we measure it elsewhere in the UK? And we went overseas to the University of Twente in the Netherlands and tested it there too. We also looked at the effect of the 3D on different size displays, the big 4-meter projection display in the lab, and 50-inch TV and projection displays, which I'll talk about briefly in a second. What time do I need to stop us? 4. Okay, I shall time myself carefully. Okay, so the experimental design was a quasi-experimental technique, meaning that we didn't have a control and we didn't have any way to randomize it, but we used this thing called a one-group pre-test, post-test protocol. Each participant was screened, so they had 3D vision, they had fairly normal vision. They were then given a set of statements which they rated their agreement with before they saw the film, and the same set of statements after they saw the film, and we looked at the change in their agreement with those statements. So the questions we presented to them were, can you rate your impression of the viewing experience 3D films can provide? Can you rate your impression of how well 3D films can convey complex visual information? Interesting in the case of big data and complexity. Can you rate your impression of how comfortable you think viewing 3D films is, because that's a big question in 3D. And can you rate your impression of how natural the sensation was? So how unnatural did it seem? How natural did it seem to you? And we also asked a question about knowledge. Please rate your knowledge of how galaxies are formed. And the way they rated their answers was to mark on this scale from 0 to 100 how much they agreed with each of these statements. So that we ran this before and after seeing the film. The first set of trials we ran with the films was in the big visualization lab in Durham with a screen about this size in 3D, and people at about the distance of the first row of chairs from the screen, which is the recommended viewing distance. And we controlled all the things about room lighting, sound levels, and viewing. And we got back a set of results on each of the questions. So from these are question 1 through 4. For all of the responses, after seeing what we claimed were high-quality 3D films, for these two films. There was an increase in their rating of agreement with the statements for the viewing experience, can it present complex information well, is it comfortable, and is it natural. You'll see that one of them was only weakly significant, which was comfort on a particular film, but we kind of expected that because the very first film we did had a sequence in it where something flew out into the audience, which was a bit uncomfortable for some people, but was an effect, 3D effect, which Mike will know well. And we had comments from people like the film seen today was noticeably more comfortable to watch than normal 3D films, whatever they are. So we were quite encouraged by those results. That was on a large screen. We then wanted to take it around to different labs and try the 3D TV. This is a plasma TV from Panasonic, I think, one of the best ones we could find. And we ran the same thing with a range of different films, and we found some disagreements, and not all the ratings improved before and after seeing the films, but some of them weren't significant. And this showed up a thing that the 3D TV manufacturers generally haven't changed even today, that there's a lot of crosstalk, light leaking from the left view into the right view, and you see these ghost images appearing, and that's showing up in ratings on comfort and on one of the films and on viewing experience, we think. And a typical comment was, we often see fine lines appear double. And if you see that in a 3D image, it's a fairly good sign that the display is not working very well. So we went to a different 50-inch display, which was the projector Alyssa has in her home, which only works in 2D, I'm afraid. But this worked in 3D, and we took it again to all three locations. And we tested a 50-inch image on this high-quality projection display with none of this crosstalk. And at that point, I'll show you more results in a second. All of the ratings improved before and after viewing the film, and all were significant or very significant. And the types of comments we got were, watching this film felt a lot more comfortable than other films. I enjoy 3D films, but often choose to watch films in 2D as they feel unnatural. This wasn't the case watching this film. So the things we were doing in the algorithms, it's not, of course, a causal proof, but we think are improving the response people have to 3D films. If you get a good quality film, people enjoy watching it, and in some sense, it's a better experience for them. Okay, across all locations, Durham, York, and 20, we got the same kind of results. There was one non-significant result, but if you ran the ANOVA, you can collapse all the data across all the sites and get a significant response for everything except question 5, which was knowledge. So at each of the three sites we went to, Durham, York, and 20, people didn't always agree, that they had improved their knowledge of galaxy formation. And that might be because at some sites we showed it to maths and engineering students, and at other sites we showed it to film studies students. And I'm not sure who it was who agreed or disagreed they'd improved their knowledge. Did the film studies students think their knowledge had improved hugely, or was it the maths and engineering students enjoyed it more and thought they'd got more out of it? But anyway, I think that was why we saw that disagreement there. But overall, of the four main conditions, when we collapse the data across all sites, then we think that we demonstrated an improvement in response to 3D films after you've seen a good quality one. So therefore, we concluded we got a significant change in audience attitude to 3D, and that we got reach to the fact that it wasn't just something that was unique to our own lab. Okay, that's evidence. And I will go through futures in the next 10 minutes. What we're looking at now is how should we start to think about visualization in the future? How should we look at new ways of visualizing things, and what new ways might we be able to obtain from the new platforms for computing, and particularly cloud computing. We've got a column coming out in IEEE Cloud Computing soon which says more about some of these things. I won't say too much about this. Some of the background to this is that I'm interested in the array of things and sensors for sensing cities, bringing in real-time streaming data, but that's not really the point of what I'm going to say. What I will say is we're very interested in cloud-based visualization, where the compute and graphics engines are in the cloud, and your local device is just a simple phone with a display, or a laptop, or a Surface, or a tablet, or even a big visualization center, but you don't have very much in the way of local graphics compute. And if that's the case, how might that change the way in which we do visualization? I'm sure those of you who do visualization are familiar with the visualization pipeline. We go from selection analytics to mapping to some geometry to rendering and to the final display. And there are two ways to do that. We're kind of proposing that we'll take an image-based approach. So all the rendering, mapping and selection analytics will be in the cloud because that's all related to the big data, and just the display and interaction will be on the client side where you are. That has a number of benefits, which I'll say now. You can target any display, you can adjust the rendering to a particular display someone has, and you don't need people with mobile phones or tablets to have very powerful graphics processors in order to produce very good graphics effects for them. We claim that will be the case anyway. I won't say much about that or that. And I've said that. But what I will say is more things about how do we think this will then change the way we do visualization. So so many people think the cloud is great for data processing. You can have huge amounts of compute and storage power to do more data processing. I think it's much better to put all that compute and data power into visualization. And what could you do if you had more visualization power available to you? So how could we improve visualization and in what ways? One, of course, is scalability, dealing with bigger problems. Another one that I'm very interested in is personalization. How can you use that additional computing power rather than just playing one movie to everybody, to allow each person to see a movie that's more personalized to their visual preferences and the performance of their own visual system. So if you have got, as I have, slightly deficient color vision, can you choose a visualization unique to me with better colors for me? If your visual acuity, as mine is with age, is degrading, can you change the resolution of the image to match my acuity or improve it for all the young grad students in the audience and put more detail in there so they can see more? Same with 3D vision. You saw the graphs with varying 3D ability. Can we tune in real time the presentation of information to individuals? Aging is a big one for Newcastle because we've got a big aging centre, but it's a part of this. If we can know people's age and personal optical prescriptions, we can do more things. But then if you make these changes to individual visualizations, what's the invariant in the visualization? What's the information in it? What's the knowledge in it that you're conveying to these people that will be the same across different types of, slightly different presentations of the same information? So there's some interesting problems there, but we could use cloud computing to power this personalization of visualization. Now the next slide's got a word on it I didn't quite invent, but it was invented by a Danish humanities person. Audiencization, which I had a complaint from my proofreader that she couldn't find it in any dictionaries. But how, equally, if you don't want to personalize it to a particular person, how do you make different visualizations suitable for different audiences? So you've got one core story, one core visualization plot line to present. How do you change that when you're doing a real-time presentation through the cloud to be more suitable for use in education and outreach? How do you change it so it's got the information technical experts would need? Or if you've got your funding bodies and politicians coming around, how do you make it a film that suits their needs better? And how do you do that all automatically? So again, we could apply the compute power of the cloud to produce these different visualizations to different people. And again, this particular one is the same question. If you're presenting information in different ways, essentially the same information in different ways, how do you know it's consistent to all these different groups of people? So, second interesting thing for me. And final interesting thing, optimization. So, as a visualization producer, the more data you guys produce, the harder it is for me to design visualizations, the harder it is for me to understand what on earth it is you're talking about before I can produce these visualizations. So can we apply computational power here to help? If you imagine visualization production as a parameter space through which I search for a set of parameters to produce the visualization which you like, can I get a computer to help me do that? Can I use an optimization search to use the cloud to produce lots of different visualizations and then define a cost function which tells me which ones might be better? So the cloud can go off, produce 100 versions of the visualization, give me a ranked list, and I can choose the one I like the most. Again, applying computing power to visualization to reduce the problem for me as a designer. This has a slightly different research question, and that's how to automate this part of the visualization process. How do you define a cost function which says that a visualization is better than another one. One example is crowding. If you've got lots of data crowded together, we know the visual system doesn't like crowding within a certain distance. So you could change the way the visualization works so you uncrowd it. We saw one with lines this morning. You might apply that to that because it could reduce the complexity in the image, and you'd know the visualization, the vision system in the human would process that easily and more quickly. But there's quite a lot of other metrics, some quite interesting ones on orientation. I have to get this the right way around. I think you're better at detecting shapes oriented vertically than horizontally. So there might be a metric in that as well. So I'm talking to a very experienced vision scientist called Jenny Reed at Newcastle about this. She researches binocular vision and has put 3D glasses on a praying mantis. And if you think that's fun, you should look at her webpage. So, okay, so that's end of my speculations. I'm going to show you one more film. This medieval universe. Okay, so I'll give you a little bit of background. This is a project with someone at Durham called Giles Gasper, who is a historian. In about 1232, Bishop Robert Grosseteste of Lincoln wrote a Latin treatise which pretty much described the Big Bang in the terms he was familiar with of the day. And so what has happened is that the Latin treatise was turned into English. The English was studied and turned into maths by Richard Bauer, one of the cosmologists at Durham, and then I visualized some of the results from that. And so this is an attempt, and I say it's a draft, it's not a finalized visualization, as you'll see, to present those ideas again in a fairly, hopefully, understandable way. Okay, find the right one. There we go.
What is the universe? How was it formed? Why did it come to be? These are questions people have posed throughout history, questions that we are still asking. One remarkable man who considered these questions and then set about trying to answer them was Robert Grosseteste. Born in about 1170, he was a scholar who would eventually become Bishop of Lincoln until his death in 1253. Although not a scientist in the modern sense of the word, Grosseteste was keen to ask questions about the world and indeed cosmos around him. As a starting point, Grosseteste made use of ancient Greek thought, mainly the writings of Aristotle, as well as Arabic and Jewish commentaries on this great philosopher. He tried to develop an explanation of the ancient universe with a reference to a Christian context. Grosseteste's universe begins. It does so with the instantaneous expansion of light, lux, from a single point. The light is able to spread itself everywhere in creation, drawing matter along with it to create the body of the cosmos. Lux carries matter until it reaches a point where the matter can be moved no further. This creates the first sphere of the universe, the firmament. Grosseteste's universe now begins to take shape. A different sort of light, lumen, emanates from the inside of the firmament, pushing forward the matter within the sphere. When lumen can extend matter no further, the boundary of the second sphere is formed. The process continues with light produced from the inside of each newly created sphere, pushing the remaining matter that is within onwards, until the point where matter will no longer move. This process creates 9 spheres. Grosseteste does not name them, but in ancient and medieval cosmology, the 9 celestial spheres are named for planets and stars: the firmament, the fixed stars, Saturn, Jupiter, Mars, the Sun, Venus, Mercury, the Moon. The 9 celestial spheres of the medieval cosmos are perfect, stable, unaffected by change. Below the Moon, the perfect order of this universe begins to break down. Light, lumen, is no longer able to reach a perfect equilibrium with matter. The universe below the moon is subject to change and is unpredictable. The sphere of the Earth is a mixture of the four elements. It consists of four subspheres: fire, air, water, and earth. According to Grosser test, water and earth remain mixed together. However, although imperfect and in a different state to those above the sphere, the realm beneath the moon is composed fundamentally of the same material. So, for Grosser test, light is a governing principle throughout the whole medieval cosmos, on Earth, as well as in the spheres above. Light fascinated Grosser test. He saw its activity everywhere. Grosser test has sometimes been thought of as the father of modern science. But we cannot be certain that he did carry out experiments. What we can be sure of is that observation and explanation of the natural world were central to his world view. However, how to reconcile ancient philosophy with the natural world in the Christian medieval context was Grosser test's main task.
Okay, so there you go. There's another 11 treatises to go on sound and colour and other things. So we've just won a 4-year grant to do that, and we'll be working on those as we go through the next 4 years. So I think I'm right in saying thank you for listening.
Perfect. So we can take a few questions, and then Nick will hang out a little bit in person in the topic. Anybody have any questions? Well,
suppose you are looking at a scene and not a movie. How many, and you're trying to construct a 3D representation, how many parameters are you actually exploring with, and what's the computational load that you really require for each of the scenes?
Do you mean in real life or in a...
In whatever you're trying to create
You mean still
in
instead of
terms
video.
of
Oh, you mean still?
visually pleasing?
Oh, wow. There's a large number of parameters that you would have to consider if you're drawing a picture of the scene. There's two ways to reduce that. One is that you know that at any one time you're only capable of holding a few concepts in your mind at once as you look at it. So you could only present, if you were designing that, you'd only present a few concepts at once to the person. So you'd reduce the number of parameters that way. In terms of total computational load, it's kind of unbounded by the size of the problem. I mean, you may have a huge data set which you're bringing down to a very small set of concepts to present on the screen. And these days, most visualization designers are working to go from very large amounts of data to quite a small amount of information and knowledge to present to a person at any one time. You can't overload. It's trying not to overload the person looking at the image with too much simultaneous information. For example, we know that if you're asked to search for blue things in an image, you'll be quick at searching for blue things, but you won't spot red things. If you're asked to look for red things, you'll be quick at spotting red things, but not spot blue things. If you're asked to search for both at the same time, you're worse than just searching for a single type of thing. So even just asking people to search for one thing at a time is a good thing to do. So there's all sorts of things that the vision scientists know very well, that visualization designers are beginning to learn these days. Colin Ware in UNH has got a great book on this.
So you did an evaluation of what looking at usually stereo movie, the parameters you have, and in some ways how effective it is. Once you give the user a knob instead of being fixed,
Sure.
do you think that is? Can you talk about the complexities of evaluating that? The stereo piece.
Okay, so we did do that in the games.
Okay.
People had a mouse and were shooting things. or were controlling the depth of things. But there was a score which we could evaluate quantitatively. To do it subjectively, I'm sure you could do the same thing. You could ask a pre-test and a post-test thing if you controlled the task well enough, so that it was possible to do that. I don't. Yeah, it depends on the interaction. There's an awful lot of different ways, as you know very well, like many ways to interact with things, and evaluating them subjectively is always hard.
But
If I had Google Glass on
Uh-huh.
and you were designing a display for me, I would think that there would be no more budget for depth than just my sitting here and looking at the whole room, where I can't see anything from here to infinity.
Mm-hmm.
Is your budget for depth due to the fact that you're spreading it over a whole audience?
No, it's an individual thing, and so Google Glass would work slightly differently. But in terms of if a screen like this is partly controlled by my depth of field, so that gives you a limit to how much you can show on the screen before it becomes blurred. But there's also a vergence limit as well.
part of it is that people don't always appreciate that you don't focus at many distances at once. You go back and forth
Yeah.
all the time. But here it's only at one
Yeah.
distance.
Google Glass is slightly different because it puts the image at infinity. So anything at optical infinity will be in focus, and up to the point about between 6 and 2 meters away where it stops being in focus, it'll be fine. But in the close range, it'll stop working probably. So they kind of put the information out there in the world rather than keeping it close to you. So it's more like, well, it's more like me looking at the back of the audience than the front of the audience. So there are. It all depends on display technologies.
Will the HoloLens make any difference?
I would be surprised. It will probably put things at some infinite distance, which might be 2 to 6 meters away.
Those of you who don't know what that is, that's this new Microsoft device where you can actually see the real world and a projected holographic world at the same time. It's not available yet. You might have one.
There are some smart people, Gordon Love at Durham and Marty Banks in Berkeley, doing electrically variable lenses, so they can change the focal plane of the image.
Yeah, is there a tie-in between my willingness to put my two eyes together on Alyssa and my focusing on Alyssa?
Yeah, because in most 3D displays, you put your eyes on Alyssa, but then focus somewhere off the plane,
Right.
if she's holding your hand out, for example.
And that's unnatural.
Yeah, that's what those ranges are measuring to an extent, although they weren't measuring that directly.
Per se?
Yes. In your section about evidence and the surveys that you did
Yep.
to the users, would it have been more representative of the visualization, understanding, or knowledge to ask questions about the content of what they're? Because at the end, based on what
You
you
give
want to
them an
know
exam.
I mean, are people understanding more what they're seeing? Is the information providing more, is converted into more knowledge?
Yeah, we could have given them an exam on cosmology, but that might have been a bit harsh.
Because, well,
But
isn't that what
if
you
it-
want to achieve? Or
We
because,
weren't
it's
trying to
different when you're-
specifically test learning, no, but we could have done, which might be another answer to Mike's question. You could have a learning task and evaluate different people, but then you have to screen them for some kind of base knowledge before you do that.
It's interesting because we've done a lot of work like that where some people here know we've done all this worldwide telescope related work, and we do some things with or without the technology, and then we ask students questions. And often, no matter how many times you try to come up with good sort of insight-driven questions, when you talk to someone, I mean, it always comes out that they're learning. That's always. But when you want to measure how much, when you talk to the people and you see kind of, oh, now I get it, which is different than, is this galaxy a spiral or an elliptical, or, some question that you can think of to ask them in advance. I too actually thought the same thing when Nick showed those questions. It's like, what, did they learn anything about cosmology? And I'm saying, yeah, people should do those studies, but I'm just saying that it's interesting that it's harder to measure that than you
I
might think.
The thing they learned was cosmology exists. as a
Yeah,
subject.
right. And then you say,
It was a goal.
Believe it or not, the state of Massachusetts has this education program where you can either have a school where, wow, I wish Aaron or Pat were here, I can't remember the words, but it's like, are the students engaged or are they learning the material? And there are some schools like Lexington High School where we're saying my children went, anyway, where the students learn a lot, but they're not engaged by science. And there's other schools where the opposite is true. And so I think what you're saying is that these people became more engaged even though you're not sure whether they learned a lot. But it's very odd to think that there are people who learn a lot of facts and just couldn't care less. But it's true. Anyway,
Strategic learners.
they do well on the exam. Anyway, well, with that note, let me thank Nick again, and he'll just say